question 25 basically says you have like a cricket that randomly hops between 4 leaves, and on each turn it hops to one of the other 3 leaves with equal probability. So after 4 hops, we want to know what is the probability that the cricket has returned to the leaf where it started. So so for this question, basically this is like a probability question. Like, so to do this problem, what we can do is we can use the normal like formula, right, that we talked about. So remember that for probability questions, like most of the time, you're gonna say probability is equal to the number of success divided by the number of possible. So remember, this is like the golden formula for probability, especially on the AMCA. You'll probably be using this formula like a lot. So first, let's calculate like the number of possible moves, right? So you have this cricket thing, and the cricket is gonna hop to like on each turn, it's gonna hop to one of the 3 leaves, right? So like right now the cricket's like right there. So like it can go to like here, here, or here. So the cricket always has 3 possible options, right? And since the cricket is gonna like hop 4 times, and on each hop it has 3 possible leaves it can go to, the total number of possible moves is just going to be 3 times 3 times 3 times 3. So that's 81. So it has 81 possible moves. So the number of success in this case is like the number of ways the cricket can start from that leaf and then like after 4 hops come back to the original leaf, right? So to find the number of successes, to find the number of ways to do that, notice that like the cricket first has to like jump to one of those 3 leaves, right? So on the first turn, it doesn't matter what leaf the cricket jumps to, like because all the leaves are like kind of the same. So like suppose that like, so let me draw like the 4 leaves here, right? So let's say the cricket is like, oops. So let's say the cricket is like right here, and let's say like it jumps to like this leaf, for example, right? So right now it's like here. So that's why we have this times 3 over here, because like the cricket can move to any of the 3 other leaves on the first turn. Whoa, okay. So, but now like when, let's say the cricket is now here, right? This red spot. Now like we have to consider multiple cases. So like there's actually 2 possible cases in this case. So the cricket is going to hop 4 times. It already used one of its hops, so it's going to hop 3 more times. So the first possible case is if the cricket like comes back to its original position, right? So if the cricket jumps to one leaf and then it jumps back, so that's one possible case. Then the cricket has to hop 2 more times to get to its original leaf. So then it has like 3 options to go to whichever leaf it wants. So like it could go to like this leaf, for example, on its 3rd hop. And then on its last hop, on its 4th hop, it must come back to its original position. So it has to come back, so times 1. So like this 3 times 1 represents like the case where the cricket like goes to one leaf, then the cricket hops back to the beginning, then it goes to another leaf, and then hops back to the beginning. So that's like one case, like this 3 times 1 case. But like there's another case, right, which is like when the cricket doesn't come back to its original position. Like maybe it decides to go to one of the other 2 lily pads. So like instead of going here, instead of going this way, what if it decides to go like to one of these 2 lily pads, right? So then there are 2 possible options. So the second case is you have to add like 2 times. So let's say like without loss of generality, since like these 2 leaves are like symmetrical, right? So let's suppose that like the cricket jumps to like this position now. So now it's used 2 of its hops, and it needs to hop 2 more times to get back to its starting position. So remember, the starting position was like this point here, right? Starting position. So now that the cricket is like here, notice that we have to be very careful, right? The cricket is not allowed to hop back to like its original position, because if it hops back to its original position on the 3rd move, then it's going to be here on its 3rd move, but it needs to use 1 more move. But if it's already at its starting position and it needs to like move 1 more time, then it has to move out of its starting position. That's like illegal. That's like bad. So hopefully that made sense. So like that means that like the cricket has to go back to like one of the remaining 2 positions. So it can either go like this way or this way. So there are 2 possible ways. So you would do times 2. So times 2. And then, so again, these two leaves are symmetrical. The green arrows pointing to the leaves are symmetrical. So let's say that the cricket hops to like, let's say hops to this lily pad here. So now it's used 3 of its moves and it has to get back to its starting position on its 4th move. So it has only one choice. It has to hop back to its original position. It's like forced to do that. So there's only one way to do that, times 1. So that represents like the number of successes. So if you were to calculate this, you would get like, and cancel out a factor of 3. And on the top, you do 3 times 1 plus 2 times 2 times 1, which is 7. And the denominator is 27. So the answer would be 7 over 27, which is just E. And so just to summarize again, like this was a weird problem. So like basically, whenever you see probability on the AMCA, the first formula you should think of is like number of success divided by the number of possible. There are other ways of calculating probability, but this is like the most common and important way you should know. So in this case, 3 times 3 times 3 times 3 was clearly the number of possible ways. And then to find the number of successes, we just split it into like 2 cases, and we like kind of carefully like simulated the process kind of and like use logic skills. And yeah, we got the answer that way.